Welcome back to the playlist for dynamic programming. In this video we're going to continue talking about rod cutting, and we're specifically going to write our DP solution for doing the rod cutting. So in the last video I had implemented this recursive algorithm, and I was spending time trying to debug it, wondering about how it was giving me a 15 for an answer, and trying to figure out how it could get 15. And then it hit me, well, you know what, if you cut it into 10 sections of 2, or sorry, 5 sections of 2, yep, there's your 15. Okay, so yes, 15 is the optimal cutting, and it's just a very boring cutting because it involves cutting everything to 2s. We could probably make it more interesting by taking the 5 and making it worth more. And the problem is that the 2 it's worth an extra 50%, so we'd have to get the 5 to be worth more than 50% additional. So how about an 8? That should alter our answer. Yeah, now we're better off cutting it into 2 chunks of 5 if we do that. Okay, so we feel good that the recursive solution is working. It gives us the answers that we expect it to have. And so now we need to change this so that it is using a dynamic programming approach. So we're going to write basically the same function as before, and I'm going to pass in same information that we had before. But with the DP, as opposed to with our recursive solutions, you have a base case. Actually, I guess before we write this, it's worth taking some note of what the order of this is. And the simple way to view this is when you do the rod cutting, you might do this cut, or you might do that cut, or that one, or that one, or that one, or that one. You can do any combination of these cuts. They're n-1 cuts, and because everyone could be kind of an on or off, that means that there are going to be 2 to the 9 possible ways to cut this, and our algorithm here is going to walk through all possible of those. So this scales exponentially, and that means if we push this up to 30, 40, 50, we're going to, well, 30 it's going to be slow, by 50 we're definitely in the it's just not going to finish type of range. So we want to use dynamic programming because with dynamic programming we're going to write something that is distinctly polynomial, and then we can scale to very large n values. So the way this works is we still like this function that we have here, but we are going to store our values into a table that keeps track of things for us. So we're going to make a vector of doubles, and I'll call it R, and R is going to have the same size, n+1, which happens to be the same size as our price array. Okay, and then I want to set the first value of that, R sub 0 equal to 0. And when we're done with this, we're simply going to return R sub n. And we're going to return the value that's at the end of this array. So we go through for each element, and we need to fill it in based upon the values that come before it. And so let's write, we need a loop for, I'm actually going to use a j here, j equals 1, while j is less than or equal to n plus j. And what happens inside of this loop? Well, it's actually going to look a lot like this. Actually, 1, 2, 3, let's copy 5 lines down. And then we'll talk about this some. So what I want to do is I want to find, this is not going to be sub p sub I, this is now sub j. Okay, so I'm trying to decide what goes into the jth element, and I'm going to make that decision based upon the things that come before j in the array. So I start off saying that the jth element, which would be, there's no cuts through the first j items, or through the first j length, that's my max. And then my loop is going to go from 1 to less than j, and instead of making this a recursive call here, we are going to look up in our array the value that we had found before. If that happens to be larger than what we found before, that becomes our max. And when we're done, I can simply set our sub j equal to max. I could shorten this code. I don't necessarily need the temp so much because this expression does not include a recursive call in here. I actually don't need, I could take away the value of max completely and just put these things inside of r sub j, and that would work just fine as well. So I could simplify this down, but before doing that, we should actually make sure this works. Hmm, 22. Oh boy. Let's look at this for auto x in R, cout x, cout inline. Zero, 1, 3, 3. That should actually be a 4. Okay, what is this doing that's wrong? We check the price of the ith element so I has to be less than j starting at 1, and we add to it, oh, that shouldn't be an n, there's our problem right there. All the n's have disappeared from inside of this loop. There we go, and this gives us 15, which is our answer. We can do the same type of sanity check that we had before. If we take the value at 5 and change it up to an 8, now I should get 16. Okay. What if we take the value at 6 and make it a 10? Then I would expect, I think 16 is our maximum answer for that, which is, yep, because we can do the 6 and then 2 3s, or sorry, 2 2s will get us there. Okay, so so here's the DP solution. What is the order of this DP solution? Well, we have two loops. There is a j loop that goes from 1 less than n, and there's an I loop that goes from 1 less than j. This type of looping structure gives you an order n squared behavior. So this is polynomial in time, and where it is order n in space, whereas the recursive version didn't, well, it doesn't declare extra variables. Turns out it's going to be order n in the call stack because it does have to do the recursive calls. This version is very explicitly order n and how much space it takes up, and it's order n squared in time. But compared to the exponential up here, we can scale this much, much larger if we needed to, and it won't have any problems with speed. So that's it for rod cutting. We'll come back in the next video and look at one more example.